Hello everyone, welcome to Schrodinger's cat and this is Devabrata. Basically, we have discussed in our previous lecture that the special theory of relativity, and today we will discuss the idea of ensembles in statistical mechanics. So today this is the lecture for thermodynamics and statistical physics, and today we will cover the postulate of statistical mechanics, microcanonical ensemble, canonical ensemble, partition function, relation between entropy and probability, classical harmonic oscillator, quantum harmonic oscillator, classical paramagnetic substance, and the grand canonical ensemble. So in our TSP, thermodynamics and statistical physics, in the IIT JAM, basically the number of questions are coming for the IIT JAM exam, approximately 8 questions. The topic is thermodynamics and kinetic theory of gas, and in JEST there are the huge number of questions are coming, approximate to 7 to 8, and the TIFR 3 to 4 questions, and for CSIR NET 6 questions, and for GATE 5 to 6 questions. This is for thermodynamics and statistical physics, and only statistical physics there are 3 number of questions are coming in each exam and every year. So basically we just now start our lectures. So basically first of all we just discuss here the introduction part, and the basically so just first one we just now discuss the postulate of statistical mechanics. So basic postulate is that the probability is defined as the PR is NR by R, and one thing is that basically we just summarize this chapter and go through the problem coming in the previous year and do homework, and after we just get time we just elaborately deduce the theory for your better concept, and for exam point of view we just summarize the chapter and problem solving session. So basically PR is NR by N, where statistical ensemble of N and NR be the system in the ensemble exhibit the entire, and basically the mean value of this, the mean value average U equal to summation over R PR and the mu R, where the PR is denote the probability of occurrence of the particular value of UR, and for the continuous systems we just get for continuous systems average of U for some change to integration rho U du, and for the dispersion we have another that the dispersion or basically defined as the variance. So it is basically sigma square average of del U whole square is basically the sum over R average U square minus U expectation square. Here is basically expectation is mil about the average, and with the Stirling formula that the ln n factorial is nothing but n ln n minus n. This is basically STIR LIN Stirling formula. So go ahead our next discussion, that the number of different ways of arranging n molecules is denoted as the n factorial, the number of different ways, and n molecule with n minus n site for defined as the n factorial is divided by n factorial n minus n factorial. and the total number of possible ways of arranging the molecule, total number of ways is 2 to the power n. So these are the basic postulate, and we have ensemble 3 type: microcanonical, canonical, and the last of one, the grand canonical. So basically first of one we just learn here the microcanonical ensembles. So first one is that if sigma is the number of accessible microstate, here one thing is that for microcanonical ensemble, so basically here the n, v volume and the energy, and so the number of microstate is defined 1 by sigma, and the accessible microstate in phase space with has energy between E and E plus D energy range is defined as the sigma integration dp dr by h cube, and in terms of energy we just write here in terms of energy Ne dE is equal to 2g pi v 2m by h square to the power 3/3 e to the power half dE. This is in terms of energy, where g is the degeneracy of the particle. So the time average of F is defined to be the ensemble average, is defined as the F average integration over tau fx b mu x, and we have the another that the S is basically kb ln sigma, where sigma is number of accessible microstate and the sigma is function of energy, volume and number of particle or number of molecule here. So exponential S by kb. This is basically microcanonical partition function. Microcanonical partition function. So relation between S and the probability, most important, S equal to minus kb sum over I pi ln pi. So different system for canonical ensemble. For 1D free particle canonical ensemble, for different system, first of one is for the free particle. So energy is function of position and momentum is defined as I to 1 to n pi square by 2m, and the partition function of n number of particle is defined for the nth number of particle is Zn equal to z to the power n 1 by h to the power n factorial twice by mkt to the power n by 2 L to the power n, where L is the integration of second integral. L means the integration of second integral is 0 to infinity e to the power minus u to the power half du, and the internal energy is basically E expectation is equal to U expectation is equal to n kBT by 2, and the specific heat at constant volume is defined del U del T at constant volume is equal to nk by 2 here. And so these are the microcanonical ensemble, and the most important is that the canonical ensembles. So for canonical ensemble we just have some most important result, that first of one it is just number of molecule, volume and temperature ensemble. So first one is partition function. So basically for the partition function here, z equal to sum over I gi e to the power minus ei beta, where beta equal to 1 by kbt, Boltzmann factor, and z sum over states and gi the degeneracy factor, and here the p of ei basically is proportional to e to the power minus ei beta, and the probability p of ei is equal to 1 by z here. And the relation between macroscopic variable and the canonical partition function, the relation is very important for MCQ type question in entrance exam. So energy average equal to U average is equal to summation over I ei pi. So it is written as in the form also that sum over I ei e to the power minus beta ei divided by sum over I e to the power minus beta ei. It is also written as in terms of z minus del beta ln z, and the another one form that kb t square 1 by z del z del t, and where the cv is del u del t at constant v. So relation between free f and z, Helmholtz free energy, and z is equal to f minus kVt ln z. Fourth one, relation between z and thermal variable or thermodynamic variables. So you just know that S equal to U minus F by T, internal energy minus Helmholtz energy by T, and P equal to minus del F del V at constant temperature. A is equal to U plus PV, and the Gibbs free energy equal to H minus Ts. So the second law of thermodynamics and interaction between the system for the is defined as the 1 by T is equal to del S del E at constant V and N. It is called that the statistical temperature. So the next thing is that for the we have deduced for the classical harmonic oscillators. So just a minute. So basically now we have deduced the classical harmonic oscillators. Yes, for the classical harmonic oscillator, so here the E each function of Q and the P is defined as the sum over I1 to N pi square by 2m plus half m omega square qi square, and qi and pi are position and momentum of the ith oscillator, and the partition function here defined f to the power n is equal to the partition function, the partition function is defined as the Zn is equal to 1 by h to the power n 2 pi mkt to the power n by 2. This is important formula. 2 pi we just now problem, so by problem we just keep in mind this formula. 2 pi kt by h omega to the power n, and the Helmholtz free energy here minus n kt ln twice pi kt by h omega. So basically last that the entropy here, the entropy is S equal to, we know, minus del F by del T at constant n and v, so it would become n number of molecule and the volume, it would become n k ln 2 pi kt by h omega plus nk, and the internal energy U F plus Ts, so it would become nkt, and the Cv it would become nk. This is for the classical harmonic oscillator. Now we just go through for the quantum harmonic oscillator here. Now for the quantum harmonic oscillator we have the same approach doing here for the quantum harmonic oscillator. So quantum harmonic oscillator, for the same thing here, the energy part is defined as just ENI is equal to sum over I1 to n. This energy become h cross omega Ni plus half, n plus half h cross omega, where n equal to 0, 1, dot dot dot. So the partition function here, the partition function Zn is equal to exponential minus h cross omega by 2 kt by 1 minus exponential minus h cross omega by kt. That would be the partition function, and for the nth particle to the power n. So here the Helmholtz free energy, here the Helmholtz free energy would become the F, we have no the minus kt ln z, just put this formula, we get n h cross omega by 2 plus n kt ln 1 minus exponential minus h cross omega by kt. And for the entropy here we just get that, just put the formula we just write earlier, nk h cross omega by kt, and you just see that all the problems coming in net and gate, and you just know that all this formula would in is written form ln 1 minus exponential minus h cross omega by kt, and for the total internal energy is equal to U n half h cross omega plus h cross omega divided by exponential h cross omega by kt minus 1, and the Cv, so basically the specific heat would become nk h cross omega by kt whole square exponential h cross omega by kt divided by exponential h cross omega by kt minus 1 whole square, and at low temperature for T low we know the H cross omega by kT would greater 1. Here the specific heat would become Nk H cross omega by kT whole square exponential minus H cross omega by kT, and that imply that each Cv tends to 0 when T tends to 0. And the another thing for the high temperature approximations, so H cross omega by kT less than 1 here, and the specific heat will become that Nk 1 plus H cross omega by kT plus dot 1 plus H cross omega by 2 kT plus dot whole square is in the form, and that imply that Cv tends to Nk when T tend to infinity. This is the classical result and the quantum behavior. Basic, this is the beauty in the physics. And in quantum energy of an oscillator is quantized. For the quantum energy oscillator, Zn would become 2 sine hyperbolic H cross omega by 2 kT to the power minus n. This is for the quantum harmonic oscillator, and we just now write some important thing for the classical paramagnetic substance. So for classical paramagnetic substances, so for classical paramagnetic substance, here the energy would become minus mu dot h, where mu is the chemical potential, and it would become minus mu h cos theta, and the partition function Zn is become 4 pi by mu beta h hyperbolic sine of beta mu h to the power n, and the Gibbs free energy here minus nkt ln 4 pi mu beta h sine hyperbolic beta mu h. One thing you just note, we have the fundamental formula, the partition function, and the relation of the thermodynamic variable, where is in the S, F and T and U and H or G. You just put this value and get this result. This is no about boring. You just first of all you just try to understand the energy and the relation between the partition function, and you to put in the value and do the derivation, and you just get the result. And after the internal energy U would become minus n mu h cot hyperbolic beta mu h minus 1 by beta mu h. So in terms of Langevin function, so in terms of Langevin function, we just Lx is equal to cot hyperbolic x minus 1 by x. So U average would become minus n mu h Lx Langevin function, and this for the average magnetic moment. Here basically one thing is that we have one notation but two meaning, and one thing I just try to say here for the classical paramagnetic substance, basically paramagnetic is magnetic behavior of the material. So here EI is minus mu h, so here mu is basically the magnetic moment, so not chemical potential. So chemical potential is in the term of proverb of the statistical mechanics, and here mu is basically the magnetic moment. You just keep in mind, and the average magnetic moment mu is equal to mu chord hyperbolic beta mu h minus 1 by beta mu h, and the magnetization is basically m is equal to n mu is equal to n mu, just put this value chord hyperbolic beta mu h minus 1 by beta mu h. So another thing is that for the quantum mechanical treatment of spin half paramagnetic substance, so this is the quantum treatment, of the paramagnetic substance. Here the partition function Zn would become Zi ith particle to the power n, so 2 cos hyperbolic mu h by kt to the power n, and the free energy is nkt ln, just put this result 2 cos hyperbolic mu h by kt, and the entropy S is become minus del F del T at constant volume. So differentiate and put this result, we get nk ln 2 cos hyperbolic within bracket mu h by kt minus mu h by kt tan hyperbolic mu h by kt. This is not you just differentiate and put in this result, and the internal energy U become minus n mu h tan hyperbolic mu h by kt, and the magnetization M would become minus del F by del H, and n mu tan hyperbolic mu h by kt, and the last one is specific heat is nk mu h by kt whole square sec hyperbolic square mu h by kt, and this is for the quantum treatment of spin half paramagnetic substance. So our last topic is the grand canonical ensemble. So basically we have for the grand canonical ensemble here, for the grand canonical ensembles, so first of one, this is basically the temperature, volume and chemical potential constant, and for the classical systems, so Zn is equal to sum over n 1 by n factorial 1 by h to the power 3n exponential mu n by kt and integration exponential of minus en function of position and momentum by kt position space integral and momentum based dq dp, and the quantum mechanical system for the quantum treatment, it would become Zn is equal to sum over n Gn the degeneracy factor and exponential mu n minus e n n by kt, and the thermodynamical quantities in the grand canonical ensemble, that the Gibbs distribution function, so rho en is equal to exponential this term mu n minus energy n of n by kt is divided by Zn, and del t is the statistical weight. Del t become the statistical weight, so statistical weight. So basically here one thing is that rho function of e and n and del t statistical weight become 1, and basically it is define del gamma, or you just write here, basically you just write del gamma. So here this is the 1, or the del gamma is equal to 1 by rho e n. Rho, the notation isn't important, but you just write del gamma, basically the statistical weight. Del gamma you just write, and after you just know the entropy definition kb ln del gamma. So put E n n by t minus mu n by t plus kb ln z mu, and f minus mu n, this term is called the grand potential, is defined minus kb ln z mu is equal to sigma. This term is called the grand potential for the grand canonical ensemble. The grand potential defines sigma, where sigma is minus kb ln z mu. So here pressure is written is in the form, go ahead our next pages. So here pressure is written in the form of P is minus del sigma by del V at constant T and mu, and S minus del sigma del T at constant volume and mu, and the average number N would become minus del sigma del mu at V and T, and the F would become Fn minus kv ln z mu, and the total energy, internal energy mu n plus kbt square for the grand canonical ensemble del ln z del t v mu. And here just two system for the classical and the quantum approaches, we just write some of them but not elaborately. So canonical is the most important. For the classical system, here For the classical system, the energy E is defined that summation 1 to 3n pi square by 2m and the potential energy QE, where this is the potential energy of the system UE, and the particle and corresponding partition function is summation 1 by n factorial exponential mu n by kt by lambda to the power 3n, where the in is equal to exponential minus u by kt. This is u by kt, and the dq1 dot dot dqn, we have 3 particle, so 3n. This is the configurable integral. Configurable integral, and this is for the classical system, and here the classical partition function would become the lambda is equal to h by root 2m pi kt, thermal wavelength, you just know in the modal physics, thermal wavelength. So basically this is the classical approach, and here the all the partition function, you just deduce the energy, partition function, microstate, number of particle, entropy, free energy, and the U, all the thermodynamic variables, all the thermodynamic variables for the grand canonical ensemble. So now quantum mechanical partition function, quantum mechanical partition function for the grand canonical ensemble, z mu is equal to summation over n, summation over capital N, degeneracy factor exponential mu n minus e n n by k bt. This is for the grand canonical partition function, and here also you just deduce 3 things: grand canonical partition function for the quantum harmonic oscillator with this formula, and the number of microstate and total number of particle. This one is the homework you just do for the grand canonical partition function. These 3 important thing, Zn, sigma and n. So now we just go ahead our problem discussion sessions. So first problem is coming in NET 2018, is saying that the variational motions of a diatomic molecule may be considered to be that of simple harmonic oscillator with angular frequency omega. If a gas of 3 molecule is at temperature T, what is the probability that a random peaked variable will be found in the lowest variable state? So we just calculate probability. So probability for, we know the, for solution we know the energy for the quantum harmonic oscillator is n plus half h cross omega, where n is 0, 1, 2 dot dot, and the partition function for the states. So first n equal to 0, half h cross omega, 0 point energy, so exponential minus h cross omega by 2 kt. Total partition function for plus 3 h cross omega by 2 kt. Next one minus 5 h cross omega by kt. Next, the probability ground state is exponential minus h cross omega by kt, exponential minus h cross omega by 2kt by sum over or total means exponential minus h cross omega by 2kt plus 3 h cross omega by 2kt plus dot. So you just common here, so exponential minus h cross omega 2kt and h cross omega by 2kt you just common 1 plus h cross omega by kt plus dot. So it would become 1 by 1 plus e to the power minus h cross omega by kt. So this would become 1 minus just reverse exponential minus h cross omega by kt. So 1 minus exponential minus h cross omega by kt. First of all, A would be our correct answer. Go ahead our next question. Second question number 2 is coming GATE 2018 is saying that, so for the partition function of an ensemble of a temperature T is given that 2 cos hyperbolic epsilon by kt. The heat capacity at temperature epsilon by k is x nk. What is the value of x? So basically you have given the partition function and you have to find the specific heat at a specific temperature. So basically this is the NET type questions in GATE exam. So NET type question is very careful for solving. So first of all, you just given the partition function z here, 2 cos hyperbolic epsilon by kt to the power n. So you know the energy relation that the kt square del ln z divided by del t. So just differentiate. So in the denominator term 2 cos hyperbolic epsilon by kt and the numerator n k t square 2 sin hyperbolic epsilon by kt and the differentiate term epsilon by kt square. So this would become n epsilon tan hyperbolic epsilon by kt. So we have to find the specific heat. For doing specific heat at temperature T just given epsilon by T, epsilon by K. So specific heat C would become n epsilon square K. Put this value epsilon square by K square sec hyperbolic square 1. So this is basically n k sec hyperbolic square 1 and it would become 0.42 n k. So implies x n k. So x would be 0.42. 0.42 would be our correct answer. Problem number 3 coming in GATE exam also is saying that the entropy of a gas containing n particle enclosed in a volume V is given by this. Entropy is given n k ln alpha V to the 3/3 by n to the 5th by 2, where n is the total energy and A is the constant and Kv is the Boltzmann constant. You have to find the potential energy. So basically you have given the entropy and you have to find the potential energy. So given we just relation that the del G by del T at constant what pressure is equal to minus entropy, and entropy is defined by minus nk ln alpha. This is given e to the power 3/2 divided by n to the power 5/2. Just put this value, so G would be, so you just minus n, you just integrate and you would get the value of G. So NKTLN, just a minute. So NKTLN, basically the alpha V e to the power 3/2 is divided by n to the power 5/2 plus ln a. Just a minute. So basically for the ln a, and you just now do the chemical potential formula, mu is equal to del G by del N. So basically put this value del G by del N with differentiation with respect to G. So K T ln alpha V e to the power 3/2, just do quickly, and n to the power 5/2 plus nkt n to the power 5/2 is divided by alpha V e to the power 3/2 into minus 5/2, just differentiate, nothing but n to the power 7/2 alpha V e to the power 3/2. So you just calculate, and after one just get the result minus kt ln alpha V e 3/2 by n to the power 5/2 minus 5/2. You just differentiate and put in the value, and A would be your answer. Mu equal to minus kt, just written thus ln alpha V e to the power 3/2 by n to the power 5/2 minus 5/2. So go ahead, our next problem coming in CSIR NET. So quick. So basically it is saying that a gas of non-relativistic classical particles of one dimensional is subject to potential this. So you have to find the partition function. So here given the potential is in the form, you have to given the partition function. So for we have write the partition function is equal to Z1 by, so you just do here that the Z equal to 1 by h integration minus infinity to infinity exponential minus px square by 2mkt the thermal energy, and the dpx, this is the minus infinity to infinity to the power minus potential alpha mod x by potential term kt dx. So here you just do this integration. So 2 pi mkt to the power half integration minus infinity to infinity e to the power minus alpha mod x by kt dx. So basically z would become 2 pi m kt by h square to the power half. You just do quick, minus infinity to infinity e to the power minus alpha mod x by kt dx. So now you just do this integration and put in the value. Do this integration, I just write homework and put in the value. So you just get 2 pi m kt by h square to the power half, and the integration value would be 2 kt by alpha, and this would become the root over 8 pi m h square beta cube by alpha square. So C would be our correct answer. So go ahead, our last questions coming in CSIR NET. A system can have 3 energy, 0 plus minus E, So you have to find the average energy. So I just write here. So for this you have to find first of all the partition function, the sum over gi exponential of minus of beta ei. So basically you have to find the partition function for the three system energy 0. So here you just get that so first of all, so you just get for the 0, this is 0, and given the doubly degenerate, this is very important. For doubly degenerate, the degenerate function 2 and e to the power 0 is 1. So basically 2 plus for doubly degenerate beta I plus e to the power minus beta I. So now taking ln z would become ln this one 2 plus e to the power beta I plus e to the power minus beta I. So one thing is that you just calculate the average energy formula. Just write in this summary form that del beta log of ln z. So you just put del beta ln, put this value z value 2 plus e to the power beta I plus e to the power minus beta I. You just quick, you just take ln of this term and differentiate with respect to beta. You just get the value minus epsilon e to the power beta I by 2 minus e to the power minus beta I by 2 divided by e to the power beta I by 2 plus e to the power minus beta I by 2. I just write quickly, and from this step to this step you just do in your homework. I just do this calculation for your home task because of for your practice, and it would help you for the exam for your speed calculation. This is basically the minus epsilon tan hyperbolic beta epsilon by 2. You just do this step in your home task. This take the ln and do this derivative, and you just get this result, and I think D would be our correct answer, minus epsilon tan hyperbolic beta epsilon by 2. So basically I usually give you to the homework for your better understandings and the concepts. You just pause the video 3 seconds or 5 seconds and take a screenshot, and you just do in your homework for better concept. And I just give you 3 problems homework in your integration part and the differentiate part with respect to beta. So basically you just do this integration and differentiation for your beta calculation and give answers, and with this value put, and after one you just check the result of the MCQ type questions. And I think you just take away the screenshot of this page. So go ahead, our next very important that solve this homework, and if you need any study material of file of my lectures, just mail with the cat Schrodinger's 1935@gmail.com. And basically thank you, stay happy and goodbye. And one thing is I just want to say that you just do the integration and the differentiation in my practical, in my problem session, which I just keep for your better understanding. I just keep for your better understanding. You just do this differentiate with respect to beta and put this value and check the result, the correct options here, and after you leave the questions. So basically I just do for your better calculation and fast and speed calculation. And so 10 questions very important in GATE, NET and some other exams. You just practice here the problem and the home task. You just do this homework and mail, and you just contact me in your this mail ID for your academic related purposes. So thank you, take care, stay happy, goodbye.